Two parts to this webinar today. I'm going to start off with an overview of what we're doing with RNA MVX, our memory virtualization product. There's some new capabilities in it in our release 2.5. After that, as Ryan mentioned, we'll have an opportunity to hear from Greg Keller about some of his experience working with the 2.5 version of the product and some of the results he's getting with his environment and his customers. As to 2.5, we've announced some new capabilities that actually extend the capabilities of memory virtualization for new applications of the technology. We've also managed to increase the performance even beyond its blazing speed of the previous release. And there are some additional capabilities in terms of making it easier to deploy and operate in any data center environment. One of the things that we think is important to look at in terms of understanding where memory virtualization fits and where we see it going in computer architecture is that there's an increasing gap between processor speed and storage capacity. And both of these are heading in great directions. Unfortunately, the memory per server is not keeping up. Even with recent gains in server memory size, the memory amount per server has not really kept pace. Storage capacity has really continued to climb, and that's a great thing because businesses are generating more and more data, and this growth rate is approaching a pretty dramatic pace. In customers and prospects that we speak with, we continue to hear that data sizes for the most active data sets that are driving the business, this is some of the information that helps businesses understand what their customers are doing, what's happening in the market. They're expecting this to double every 12 to 18 months. On the other extreme, processes continue to grow at a pace that's following Moore's law, and so simultaneous with cramming more cores in per socket, and there's an increasing clock speed. And this also is great because this means that the amount of analysis that we can do to extract value from all this great data is increasing as well. The problem is that memory is at a tremendous disadvantage. And when I say memory, I'm talking about RAM inside of the server. Because even with the recent increases with server size, server memory size, it's been announced by different platform vendors, it's really not enough, and it's not keeping pace either with the amount of data that businesses are collecting and generating, or the amount of processing that the processes can actually do to do analytics, modeling, and the like. And this is where we see the need for a new tier of memory, a new tier for storage and management of active data really comes into play. We see memory virtualization as fitting in between storage and server virtualization. And when we talk about memory virtualization, we're talking about what happens with virtualization in general, which is converting a physical resource into a logical service. Now, memory virtualization is a little different than, say, for example, server virtualization. Server virtualization is about splitting things up, basically taking one thing and turning it into hundreds. Memory virtualization is really aggregation. It's about taking 100 things and turning it into one. So it actually creates a large central resource that sits between storage and servers. Memory virtualization is interesting as well because it's different than other virtualization in that most virtualization is expected to come with some kind of performance cost or some kind of hit to how fast things work, because you're getting some kind of increased manageability as a result. So that's an okay thing. On the other hand, memory virtualization actually accelerates application, and it does this in two ways, and it does this in a way to help out both storage and servers in that it makes servers look bigger and storage go faster. So by making servers look bigger, it actually is extending server memory. And by making storage go faster, it's giving you a place to put more active data into the compute tier. And that's where we see it filling in the gap. If you look at what memory virtualization does, it basically is creating or aggregating this memory across servers, server memory, and creating what we would refer to as a memory cloud. Now, this is a private cloud solution. It's based purely in software. It uses standard servers, RAM, networking to work, and it basically decouples memory from the bounds of the physical box. This results in a resource that's actually very, very high performance. As a matter of fact, in terms of latency, this actually can deliver memory from one server to another in about 1.7 microseconds. So that's considerably faster than what you get with disk storage, even local disk storage at millisecond rates. Also, the throughput of this can come close to 3 gigabytes per second per server. And in aggregate, it actually ends up being much more than that because it can service multiple servers at the same time. So this new distributed service actually provides a very high performance new tier of memory for servers for a number of uses. Also, it opens up some new models in terms of costs for both the infrastructure in terms of IT economics as well as business value with its resource. On the cost side, because it's based purely on commodity hardware, it's much more effective than either buying bigger servers or adding more cache memory to storage. And it has the advantage that once it's in place, it's extremely flexible. This flexibility then allows you to simultaneously deploy the resource to meet a number of different business-specific needs. And so you can create a much better connection between the actual business value that you're creating from the resource and the actual resource itself. As an example of this, and Greg will talk about some of the examples in his environment, but as a separate example from this, we're actually able to work with the customer to create a multi-terabyte server created from dozens of existing mid-sized servers, and it resulted in a specific increase of a large bioinformatics application that allowed it to run much larger data sets than it had ever run before. And this was actually at a savings over $1 million in server upgrades to be able to try to get the same kind of result. So we see these kinds of results over and over as people can create memory clouds directly from these commodity components. The last piece of that is completely transparent through deployment. So it's actually a technology, just like any virtualization, it's completely transparent to the client application, the guests that are using it. So there's no change to applications, no changes to application code to actually get it to work. Some of the specific types of applications then that we see this for are in, again, data-intensive environments. This is really an area where we see, again, that there's a lot of things that are driving this doubling of data every 12 to 18 months. Some of the things are capturing more historic data from the market. Other things are the drive to get more instrumentation on the actual customer interaction, either online or through direct communication. Other things are that we're starting to see are actually increased instrumentation of the business processes themselves. And all these things create very large data sets. We're also seeing, though, that memory virtualization can have a significant impact on smaller data sets where the amount of analytics and modeling itself needs to be run more quickly. The results are having a shorter shelf life, and there's more opportunities to get benefits even out of smaller data sets when you can move them into the compute tier to do more frequent processing on them. Also, when you look at the virtualization of the data center, there's a number of benefits in terms of what we could do with memory virtualization. Again, to make large servers or servers look larger and also storage go faster. And again, with memory virtualization, we can provide both. Another example is just in utilization of virtualization to support test and development environments. We've been able to supercharge these kinds of systems to allow these test and dev or the product lifecycle to run totally contained in the memory cloud and run much, much more quickly. And I'll show you some actual numbers around that in a second. So just to give you some specific ideas then on how the cloud gets used, it can make storage go faster. That's what the product has done in the past. And with this memory caching, it actually allows for access to data at up to in-memory speeds. New to 2.5 is the ability to actually extend server memory. We talk about this as memory motion, basically the ability to move memory to the actual server rather than trying to move the application to a server that's got enough memory. And we can actually create multiple terabytes of memory in this case. And the way this works is actually that the memory is available as an extended high-speed swap. So if you think about this, this is the most general purpose type of solution for making servers look bigger, in that it works directly with the OS and the application as they work today, and basically make it so that swap is actually fast, swap's actually good, again, by creating this new tier of storage right in the compute tier to support the actual application server. And finally, we get some interesting use cases around using the cloud itself as a memory store to accelerate computing in general. And this can be extremely useful in test environments where you want to accelerate the actual application lifecycle. An example of this might be model back testing for financial trading models. This can also be very useful as a scratchpad for applications that create large amounts of intermediate results. Examples of this would be job scheduling or technical applications, for example, like finite element analysis. And finally, the memory store can be used to solve software and image distribution problems. Again, providing dramatic offload for the storage tier by moving images or moving software into the compute tier for distribution across all the nodes. I'll turn quickly to some specific examples of numbers. This example is one where we basically used memory motion to make a server look larger. And what we did was we started with a server that had enough memory for the entire working set. You can see here that 83% of the working set was the size of the working set relative to physical memory. Then basically we cut the memory in half and went to a scenario where the working set was actually over 160% of the actual physical memory. You can see here that the performance in gold of the application running on top of MVX roughly stayed the same, whereas if the application started to swap, it ran roughly 20 times slower. And this was true with either SATA disk or with flash drives. Again, flash drives do not perform well in this scenario simply because of the write performance. In the third scenario, we actually cut the memory in half again. So now we're over 300% of a working set size to physical memory ratio. And you can see here again that the performance of the application in MVX stayed very much the same versus what happened when the application began to swap. And so you can see that basically we're taking standard servers, or taking servers that are only a quarter of the size of what would be needed to run the application in memory, still we're able to develop or produce dramatic results. And this is very useful not only for running applications that may need memory on an actual basis, but also for applications that might have spikes in needs or usage, as might occur in, say, a virtualized environment where you have a number of applications competing for memory resources. As another quick example, if we look at the memory cache scenario for applications, as the amount of working data goes up, you get these dramatic improvements. And there's two things to really see in this particular graph. Not only is the performance of accessing the data from the memory cloud much faster, it's also much more predictable because it's not depending on storage or competing with other applications for storage bandwidth, for storage resources. You get a very consistent performance with the memory cloud that you don't get with storage. This also has a side benefit that the other applications that are still working against storage for general purpose file capabilities are basically getting the benefit of the offload of the active data out of the storage tier. And as a last example of the memory store scenario, this is an example of creating a complete environment for an application entirely in the memory cloud. In this case, it's actually SQL Server. It's actually running the OSDB test, and in this case, this is the results for the multi-user OLTP test. On SATA disk inside of a VM, you're getting about 53 tuples per second throughput. This is pretty typical. If it wasn't inside of a VM, it would probably be getting about 100 to 150 per second. But here we're running MySQL inside of a VM with all storage and everything inside of MVX Cloud. And suddenly we're getting 65 times performance improvement. So basically we're getting in-memory performance with a standard open source database. Just to summarize some of the other capabilities, again, with MVX 2.5, we achieved performance improvements over previous versions, so it's getting us to some of the striking performance gains. We've also done some work based on feedback from our customers to help with the installation. It can install in minutes, very easy to configure, very easy to do automated update from a centralized point. We've also done some things to improve the range of security models supported, so it makes it easier to put it into any kind of computing environment.